So we just finished looking at exponential equations. Now we're going to look at logarithmic equations, starting with the base case of a log equal to another log. So notice, just like with exponentials, we do have a nice little cheat sheet of steps here, but we're not going to have to worry about that first step just yet. Notice there is nothing to condense for this first problem. So we can jump right down to number 2, the one-to-one property. What the one-to-one property tells us is that if we have two logs with the same base, then we can just go ahead and set their inputs equal. We used the one-to-one property for exponential equations. It also works right here for logarithmic ones. So if we actually look at example 1, I have a log base 5 on the left and a log base 5 on the right. So just like with exponentials, I can set those insides equal. Again, that's our one-to-one property. Quite nice. This one's actually fairly trivial to solve. It's a pick on the little guy problem. 5 is definitely smaller than 6, so I can subtract 5x from both sides, and that will leave me with a 9 on the left. 6 minus 5 is a 1, so I'm left with just 1x on the right. Now we want to check for extraneous solutions, and this is where things can get tricky. Our third step here, checking. I want to show you why checking for extraneous solutions is important for logarithms. Note that if I take a log, and this is just a log base 10, a plain old boring log, and I try to put a 0 into that logarithm, I get a domain error. I am not allowed to put a 0 into a logarithm. Moreover, I'm also not allowed to put negative numbers into a logarithm. Error, non-real answer. So we need to be careful with logarithmic equations because extraneous solutions can come about. So if we take a look at number 1, we claimed that x was 9. We want to double check that that actually works. So if x is 9, then log base 5 of 5x, and again, x is 9, so 5x plus 9, that should equal a number. Nice, I did not get a domain error or non-real answer. That should equal the same thing I get on the right-hand side. On the right-hand side, I have a log base 5 of 6x, and again, x was 9. These should be equal. Lo and behold, we're good to go. I got the same thing on the left as I did on the right, so that answer checks out. That one is good. Let's take a look at one with slightly more algebra. Looking at number 2 here. Note that I have a log base 2 on both sides, so I'm good to use our one-to-one property. This is another pick on the little guy problem because I have variables on both sides. So negative 4 is my little guy. I can add 4 to both sides to get rid of it. And if I'm moving all my variables to the right, I might as well move my constants to the left. So we'll have a 1 take away 43 on the left-hand side. And on the right-hand side, we have the 2n plus 4n, which gives us a 6n. Go ahead and divide in blue. Dividing both sides by 6 gives us a negative 7 for n. So once again, we want to check that negative 7. We want to make sure it's not extraneous. So jumping back to the calculator to check, if n is indeed negative 7, then I should be able to take log base 2 of 1 minus 4 times x, and again, x is negative 7. And I should get back a value. Again, if I hit enter and it tells me no solution or domain error, then that means I did something wrong or that this is an extraneous solution. But look, I got a number. That's a good sign. Then alpha F2 brings up my log base menu again. I can now check the right-hand side. The right-hand side was 2n plus 43. Lo and behold, I get the same number for both sides of the equation. So this solution does check out. So we should probably look at an example which does have an extraneous solution to show you that they can happen. If we take a look at this well, not the very last one, but take a look at number 3, the last one for this video. I have common bases. That's good news. That tells me that 6 minus 3w is equal to negative 2w. At first glance, it doesn't seem too much different than the first one. We can add 3w to both sides. And that tells me that 6 equals w, because negative 2 plus 3 is 1. So let's go ahead and see what happens. If w is in fact 6, then on the left-hand side, I should be able to do log base 9 of 6 minus 3w. And again, w is 6. Non-real answer. We can stop right here. Note that if we go back and double-check all of our steps, they are good, but it gave us a value, this 6, which breaks the domain of the logarithm. Because if I try to put a 6 in for that w, I'll get 6 minus 18. That's a negative number, and it does not work. So this equation actually has no solutions. So be on the lookout for those extraneous values. They can show up in this unit just like they did for rationals. Go ahead and try the practice problems. When you come back, we're going to take a look at logarithmic equations, which require some properties. Again, that's that step 1, the condensing of logarithms that we've been skipping, because we haven't needed it yet. But try some practice, and then come on back for some more hard work.